Hi there, welcome back. In this class, we changed the topic of our discussion for the moment. That is to say, we move from extreme value theory towards another branch of statistics, that is time series. So we will see the basics of time series analysis. Obviously, as for extreme value theory, in time series, we will not deal with all the little details and the many fascinating things we could say, but we will just pick what we will need to address market, credit, operational, liquidity risk, and friends. So if you want to go deeper into time series, I will give you some references. For example, on Brightspace, you will find a wonderful book that you can for sure exploit. And in that book, I will just ask you to read some parts within our course in quantitative risk management. Now, time series analysis is an essential part of statistics. It has some features that are specific to time series, and we have to adapt concepts coming from other branches of statistics to the analysis of time series, and also to introduce new tools that are commonly not used in other branches of statistics. And it is essential because most of the observations we play with in risk management are actually time series, so collections of variables and observations over time. In this class, we will introduce the basics of time series, so we will discuss a little bit quantities like the autocovariance, the autocorrelation. We will define what stationarity is and why we need that. We will see how to play with the trend of a time series. The things we will consider in this lesson and in the next lessons will be extremely useful when later we combine time series and extreme value theory to try to address real world problems, so real life problems that are the goal of our analysis. So we really want to be able to play with risk in a financial portfolio. Okay, let's try to give a definition of time series that can be useful for us to start our investigations. We call time series a sequence of data points that are indexed by time. In more details, a time series is a sequence of points that has the following characteristics. It is made up of different measurements that can be repeated measurements made over a given time interval for a given phenomenon, and at each time unit in the time interval corresponds only one data point, so only one measurement. We cannot have for the same time unit two or more measurements. This is extremely important. A time series is said to be equally spaced if the measurements over time follow a fixed pattern. So, for example, we measure the temperature in my hometown every morning, every day. Okay, so we have daily observations. Every day we have one data point corresponding to the temperature in my hometown. A time series is not equally spaced if, conversely, we have the measurements in time, but the distance in terms of time units is not constant. So, for example, we have an observation of the temperature today, then we have an observation after 1 week, then we have a third observation after 2 days, and then we have a fourth observation after 1 month, and so on. So there is no regularity in the time units at which we observe the phenomenon. Now, playing with an equally spaced time series is much more simple than playing with an unequally spaced or not equally spaced time series. Here we will focus just on the first situation, so equally spaced time series. Please notice that equally spaced does not mean that we always have all the observations. So we might be in the situation in which for some days, some hours, some years, some months, depending on the time units, we don't have an observation. So we have a missing observation. But the idea is that a missing observation is just a lack of observations in a regular pattern of observations over time. So I have a daily time series, and then on Thursday of that particular week or on Monday of that particular month, I don't have an observation for whatever reason. In that case, we treat the observation as a missing value, and there are techniques like, as we already said when we were making the difference between an outlier and an extreme. For example, we can average. So there are tools to deal with that. An unequally spaced time series, conversely, is not just a collection of missing values. It's really that, for whatever reason, we have measured the phenomenon at different time units without following any specific pattern. You can imagine that there we also have to take into consideration the structure of the time units. Maybe we have to impose a model for the measurements over time, so it's much more complicated. While time is commonly assumed to be a continuous random variable, even if you enter into the philosophical and the physical discussion about time, you can discover many interesting things. That's why I'm suggesting you the reading that you see on the slides. In time series, at least at the level of time series that we consider here in this course, for us time will be discrete. So if we are observing a given phenomenon, we will have discrete time observations for that phenomenon. And the time series, again, I repeat, will be equally spaced. In time series, there are many different types of time series that you can actually play with. A very important distinction that we will consider later in this lesson is the distinction between stationary and non-stationary time series. One thing that you can already register in your memory is that it is always easier to play with a stationary time series. That's why, for example, in modeling prices or the behavior of a stock, we prefer to play with the returns and not with the prices directly. Why? Because typically returns and losses expressed in terms of percentage are stationary, while the price themselves are not necessarily, and actually we can say are never stationary. There are different ways that we can use to describe and analyze a time series. We will see together quantities like the autocovariance, the autocorrelation, and then obviously the ACF, the PACF. We will see how we can impose models. But a fundamental question that we have to ask ourselves is, what is really the most important thing in analyzing a time series? Actually, when we are studying a time series, at the end of the day, we are interested in the so-called finite-dimensional distribution of the time series. That is to say, if I'm observing a phenomenon over time and I have these repeated measurements of the phenomenon, I'm interested in considering the joint distribution over a given time interval of all the different random variables that will correspond to the realizations of the phenomenon. In a sense, it's like, imagine we have 1 week of observations, so we have 7 observations. What we are saying is that we are considering a collection of 7 random variables. Every random variable will, in a specific day, get one value, that is the value we observe. So at the end of the week, we have a collection of 7 random variables, and we are interested in knowing what is the joint distribution of these 7 random variables. In time series analysis, a very important quantity is the autocovariance. Given a time series process xt, the autocovariance is nothing more than the covariance of xt with itself in the past or in the future. We would say that the autocovariance is of order 1 if we consider xt and xt minus 1 or xt plus 1, of order 2 if we consider 2 legs, so xt and xt minus 2, and so on. So the autocovariance of order h is when we consider xt and xt minus h or xt and xt plus h. Estimating the autocovariance in a time series from an empirical point of view is very simple. The formula is on your screen, and it is nothing more than the formula you would also apply in terms of covariance in a generic data set. Only notice that we do not divide by n minus h, but only by n, and this is due to numerical reasons and also reasons related to spectral analysis, which is a sub-branch of time series, but we do not enter into the details. One very important thing that is to be underlined is the symmetry in the autocovariance, which is something that it is inherited from the properties of the covariance. So if I consider gamma of h is exactly the same value I get for gamma of minus h. So it is not important if I consider lags with respect to the past or the future. Given the autocovariance and so the autovariance, and if you want the auto-standard deviation, then as we do with the variance, the covariance, and the standard deviation, we can compute the autocorrelation. The autocorrelation, as the standard correlation we are used to play with in other branches of statistics, is a quantity that lives between -1 and 1. The stronger the correlation in absolute terms, so the interpretation is exactly the same, the stronger the correlation in absolute terms, the more we can say something about xt plus 1 just looking at xt, or the more we can say about xt by looking at xt minus 1. For example, if we are considering an autocorrelation of order 1. In generic terms, if the autocorrelation of order h is very close to 1 or -1, it means that the linear dependence between observation xt and observation xt minus h is very strong. And so we can actually say something strong about their connection. That, by the way, would be of the linear type in this setting. We are playing with the correlation, so it's a linear measure of dependence. But this information is extremely useful from a predictive point of view, if we want to make predictions about the future behavior of the phenomenon we are considering. Please notice that a very important assumption we are making, even if not yet explicitly, is that the variance of our phenomenon is defined. So you can already think about what could happen in the case of fat tails, in which maybe the variance of the phenomenon we are considering is not finite. Immediately, if the variance of the phenomenon for which we are computing the autocovariance, the autocorrelation, and so on is not finite, then these quantities are not defined. And we have to think about something else. Okay, so that's very important. Remember that for the moment we are considering the situation of a phenomenon that at least has a finite mean and a finite variance. We will see later what happens when we remove this. If you study the behavior of the autocorrelation for different values of h, so if you look at the behavior of the autocorrelation for different legs, so h equal to 0, 1, 2, 3, 4, 5, and so on, and you plot the value of the autocorrelation with respect to the different legs, you obtain the so-called autocorrelation function, and graphically speaking, the so-called ACF, or the autocorrelogram, which is an extremely important tool that we will use to study time series. We will see that learning how to read an autocorrelogram is very important to have a quick grasp of the behavior of a time series. While the autocovariance is the covariance of the phenomenon with itself in the past or the future, so if I consider my observation xt, I'm interested in knowing what is the covariance between xt and xt minus 1 plus 1 minus 2 plus 2 and so on. If I have two different time series, I can introduce a generalization of the autocovariance and of the autocorrelation. An example is, for example, the cross correlation. That will be the correlation between two different time series. Now, we will not use a lot the cross correlation in this course, but nevertheless, it is important to know that it exists. And if you are attending, or you have attended, or you will attend a course in time series, you will see that the cross correlation can be extremely important for the analysis of your joint time series. Let us now consider a very simple exercise involving one of the basic processes in time series, a process that we will consider in more detail later, but that we can already introduce. This is the so-called moving average process. And in particular, we will consider a moving average process of order 1, in which, in other words, we just consider one lag in time. Okay? When we say order 1, order 2, order 3, we are considering how many lags are important in the definition of our process. So we will consider moving average of order 1, and for that process we are interested in computing the autocovariance and the autocorrelation. The results of this exercise are available at the end of this video lesson, but I suggest you not to have a look at the results before trying yourself. So consider the moving average process of order 1 defined as xt equal to wt plus theta times wt minus 1, where the quantity wt is a white noise with mean 0 and constant variance sigma square. Moreover, the different white noises wt, wt minus 1, wt minus 2, or wt plus 1, wt plus 2, and so on are uncorrelated. This is very important. Now the questions are, what is the autocovariance and what is the autocorrelation for this process? If you don't remember the definition of white noise, I can give you an intuition. It is extremely simple. Imagine to have a collection of random variables w1, w2, w3, and so on. Now, we call this collection of white noise if the expectation of all the random variables is 0 and if they share the same constant variance. So we are considering an homoscedastic situation in which the variance of W1 is sigma square, the variance of W2 is sigma square, the variance of W3 is sigma square, and so on. Moreover, we assume that the different random variables W1, W2, W3, and so on are uncorrelated. Now, a collection indexed by time of random variables that have expectation 0, constant variance, and they are uncorrelated is called a white noise. This is an important benchmark in time series and in engineering because it's a very simple way of representing a random type of error, a random type of noise in a time series. That is to say, at the end of the day, when we study a time series, we want to be able to extract all the information possible, and the remaining part, what we cannot explain, needs to be a white noise. So just a sort of error due to randomness that cannot be further modeled. One important thing that I want to stress is that while it is true that a white noise in time series plays more or less the role that normally distributed residuals play in standard regression analysis via OLS, in reality there is no necessity for a white noise to be constituted by normally distributed random variables. So I know that it is a common assumption, but a white noise is just a collection of random variables with mean 0, constant variance that are uncorrelated. The fact that W1, W2, or W3 are normally distributed is something extra. It is not necessary for a collection of random variables to be called a white noise. When modeling a time series, we like to play with stationary time series. That is to say, a time series that satisfies the property of stationarity. We will see that we can give different definitions of stationarity: strong stationarity, weak stationarity. There are also other definitions, but we just focus on these two basic ones. Now, why it is important to have a stationary time series? Because for a stationary time series, the analysis, and in particular the prediction of future values, is easier. So what we always try to do is to start from a time series, and if the time series is not stationary, we try to make it stationary. We will see that we have different approaches for trying to do that. We are not always successful in making a time series stationary, but we try to do that. We can also play up to a certain point with non-stationary time series, and also there we will see something in the next lessons, but non-stationarity can be a problem. In particular, we will see that non-stationarity can be a big problem if we are interested in the maxima of a time series. So if we want extreme value theory to kick in our analysis. We say that a time series is strongly stationary if the finite dimensional distribution is immune to time shifts. What does it mean? It means that if I have some observations from my time series, say xt1, xtn, and I look at the joint distribution there, then if I shift all the observations by a factor h, then the joint distribution remains the same. So we have this equality in distribution. So the distribution of xt1, xtn is the same as the distribution of xt1 plus h, xtn plus h. Now, strong stationarity is a strong requirement that is rarely verified in data. So it's not very operative for us in risk management and in the analysis of financial time series. Strong stationarities have important implication in terms of the autocovariance and so on, but we do not enter into the details too much because it is not very plausible for our analysis. We therefore prefer to play with weak stationarity. So we say that a time series is weakly stationary if the mean of the time series is constant. So if I take the expectation of xt, this is equal to a value mu that does not depend on t. And if I consider the autocovariance, this autocovariance is immune to shifts of the observation. What does it mean? It means that if I consider the autocovariance between xt and xt plus h, then this autocovariance is exactly the same autocovariance that I can compute between x0 and x0 plus h. As we shall see in actual data, there are many causes of non-stationarity that we will try to remove. As we shall see in actual data, in real life, there are many sources of non-stationarity that we will try to remove so that we can play at least with a time series that is weakly stationary, because that simplifies a lot our analysis. We will see that common causes of non-stationarity are trends, seasons, so seasonality in the data, and structural breaks. A trend means that there is, for example, a linear trend of growth in the time series or a decreasing trend. Seasonality means that there are some seasonal effects, like, for example, you can imagine that if I measure the temperature, the daily temperature in a given city, and I'm in the northern hemisphere, then what I have that during summer the temperature is typically higher and it is lower in winter. And this is a pattern that I will observe over time. So I want to remove that information because that information will necessarily influence the mean of my phenomenon, the average temperature, okay? So, and that introduces non-stationarity. Another problem is a structural break. So imagine that there is a time series and then for whatever reason, there is a big jump in the time series and then the time series continues. That it's a complicated thing to model and we have to try to find a way of dealing with this big jump. Okay, now I'm oversimplifying a little bit, but let's say that trends, seasons, and structural breaks are three sources of stationarity that we want to take care of. Okay, as promised, I give you the solution to the autocovariance autocorrelation exercise related to the moving average of order 1. You just find the solution in the next slide. To compute the autocovariance of a moving average of order 1, you just have to recall two things. First of all, the quantity Wt is a white noise, so it has mean zero and a constant variance, and there is the property of uncorrelation of Wt from all the other Wt plus 1, minus 1, and so on. Given the presence of the white noise, computing the expectation of the process xt is extremely simple. That expectation is just 0. And the fact that the expectation is 0 simplifies a lot the computation of the autocovariance. Now, what you have to find out is the functional form of the autocovariance, and what you have to do is to verify what is the value of the autocovariance for different h. So for h equal to 0, you find that the value is 1 plus theta squared multiplying the variance of the white noise, so sigma square. For h equal to 1, you find out that this is just theta sigma square. And for all the values of h larger than 1, actually the autocovariance is just 0, because the different values of our white noise, Wt, are uncorrelated in time. Once you have the autocovariance, computing the autocorrelation is extremely simple, and I leave that computation to you. So at the end of the day, what you just have to do is to apply what you know about the white noise and remember the linearity property of the expectation, that is a linear operator, and so enters and allows us to simplify a lot of things in our computations.